Hi everybody, Mrs. Pesic here. We're looking at section 3.5, exponential and logarithmic models. The learning objectives are to use exponential growth and decay functions to model and solve real-life problems. Also use Gaussian functions, logistic growth functions, and logarithmic functions to model and solve real-life problems. So the 5 most common types of mathematical models involving exponential and logarithmic functions are the following. So there are exponential growth models, exponential decay models, Gaussian models, the logistic growth model, and logarithmic models. All right, everyone should have a 3.5 gift that has these on it. And if you would take a look at page 257, you'll see the basic shapes for these graphs. So on page 257, you see that exponential growth, that's this one right here, modeled by this. The exponential growth model would look something like this. All right, and you also see the exponential decay, that's this one here, that graph looks something like this. All right, both of those have horizontal asymptotes at y equals 0. All right. Next up, the Gaussian model. The Gaussian model is kind of looks like what you might have heard of as like a bell-shaped curve. It kind of looks like that. So the bell-shaped curve, the graph looks something like this. It also has a horizontal asymptote at y equals 0. Then we have a logistic growth model, and that one's kind of an interesting, different-looking graph for the logistics growth model. That one kind of starts out small, then it kind of grows rapidly, then it starts decreasing its growth, and it levels off again. So this one actually has 2 horizontal asymptotes. And then lastly, that's the logistics growth model. And then lastly, we have, now they've written all over this, we have the logarithmic models, but you know what those graphs look like. We've been looking at those. So the logarithmic models, you know, look something like this, whether we're talking about natural log or common log, and those guys have a vertical asymptote. All right, let's take a look at the first example from your gift. The population P of a city is given by P equals 95,300 times e to the 0.055 t, where t equals 0 represents 1996. According to this model, when did the population reach 150,000? So you know how to solve these. We're going to plug in 150,000 for P, and we're going to solve this equation for T. So in this case, we will divide both sides by 95,300. And this is a real-life problem, so it's okay to get a decimal value. So 150,000 divided by 95,500. $150,000 divided by 95,300. I'm getting 1.574. I'll say 1.574 for this. All right. So 1.574 equals e to the 0.055 times t, and then we're going to have to rewrite this in log form. So this is going to be log to the base e of 0.055 t. No, that's not right. Log to the base e, sorry about that, log to the base e of 1.574 equals 0.055 t. And at this point, we need to just divide both sides by 0.055. So if we do this on our calculator, I want log to the base e, which is ln. So I can just do ln of my previous answer, control e to the x of control answer, and then I'm going to get out of that parentheses, and I am going to divide by 0.055. divided by 0.055. I am getting 8.24. So if 8.24 is going to be my t value, and the question that we were trying to answer was, when did the population reach 150,000? Well, in about 8.24 years, and that'd be from 1996 plus 8.24. So we're really talking about, what, 2004? Really, maybe we'd want to round up and say it's going to happen in 2005, you know, because we're rounding up. When did it actually reach this population? Well, it didn't reach that population until maybe 2005. Okay, let's take a look at something else. In a research experiment, a population of fruit flies is increasing according to the laws of exponential growth. After 2 days, there are 125 flies. After 4 days, there are 350 flies. So how many flies will there be in 6 days? All right, so let's think about these ordered pairs. 2, 125, 4, 350. And they're growing according to the laws of exponential growth. So let's go back to our formulas, which were on our first page. Exponential growth model. You can hardly see it because I scribbled all over it. Let me clear some of this stuff off. So we're talking about this model right here. All right, so we want A times E raised to the bx. So right here, I am going to write down y equals A times E raised to the bx. Notice that we are using the natural base E for this, okay? All right, so with this in mind, let's plug in what we know. We're going to plug in 2 for x and 125 for y. So I'm going to have 125 equals A times E raised to the b times 2. Okay, and I can also plug in what 350 equals A times E raised to the b times 4. All right, well, that's good to know. Let's at least take this first equation here and maybe solve for A. So I can divide both sides by e to the 2b, right? This e to the 2b divides out with that e to the 2b. And so I get an expression for A that is 125 over e to the 2b. And now, using a little substitution, we can plug this right in here for this A in the other equation. When we do that, we're going to have 350 equals 125 over e to the 2b times e to the b times 4 is just 4b. So I can think of this as e to the 4b over 1, and notice I really have 125 times e to the 4b over e to the 2b if I kind of rearrange what I have here. And I think with this in mind, I can solve for b. Well, what is e to the 4b divided by e to the 2b? Well, you know the properties of exponents. Like if I have, x to the 6th over x to the 2nd, I'm dividing two numbers with the same base, I'm going to subtract and get x to the 4th. So I want to do the same thing here. I'm going to do e to the 4b minus 2b, and I'm going to get e to the 2b. 4b minus 2b is 2b. So far I have e to the 2b times 125 equals 350. And let's divide both sides by 125. And we get 350 divided by 125. 350 divided by 125. I'm getting 14/5, which is approximately 2.8. So this side is 2.8 equals e to the 2b. That's in exponential form. Let's rewrite it in log form. So this is going to be log to the base e of 2.8 equals 2b. All right, and that's the same as saying ln of 2.8 equals 2b. So dividing both sides by 2, we get ln of 2.8 all over 2 is going to be our b value. So let's get a value for that. ln of 2.8 divided by 2. So I want ln of that answer, ln of my answer, which was 2.8. Right click, and I want to divide that by 2. Right, ln of 2.8 divided by 2. And so I get 0.5148. So let me write that down, 0.5148. 5148. So now that I know the b value, I'm going to go back up and I'm going to plug it in way up here where I was solving for a, or where I have an expression for a. So that b value, which is 0.5148, is going to go right in here for that b value. And so I'm going to write down somewhere, if I can find some room, a equals 125 over e to the 2 times 0.5148. That's going to be my a value. Let's get a value for that. This is 125 over, let's do fraction templates. I want 125 over e raised to the 2 times 0.5148. I really could do 2 times and then do my last answer, which I had there, 0.51481. So control answer, and so I am going to get 44.64. I'll just round it like that, 44.64. So that's my value for A, 44.64 it turns out to be. So now that I have my A value, 44.64, that's going to go in right here. And my B value that I found, which was 0.5148, goes in right here, 0.5148. So that means my model, I'm going to write my model here. The model is going to be y, that's supposed to be my arrow, y equals 44.64 times e raised to the 0.5148x. Great, now that we have the model, we can finally answer the question, which was, do we remember that this problem was about fruit flies? How many flies are there going to be in 6 days? Now that we have our model, all we need to do is plug in 6 for the number of days, which is x. All right, so I am going to enter that, 44.64 times, I need e, oops, I don't want that, delete. I want e, that's not good either. 44.64 times e to the 0.5148 times 6. There's going to be about 980 fruit flies. About 980 fruit flies on day 6. 980 fruit flies on day 6 to answer that question. All right, I like this problem. This is a nice problem. All right, let's see what else. Let's talk about carbon dating for a moment. And let's take a look at the top of page 260. On the top of page 260, they give a little bit of background here. It says, in living organic material, I hope you're all on page 260 with me. In living organic material, the ratio of the number of radioactive carbon isotopes, that's carbon-14, to the number of non-radioactive carbon isotopes, that's carbon-12, is about 1 to 10 to the 12th. When organic material dies, its carbon-12 content remains fixed, whereas its radioactive carbon-14 begins to decay with a half-life of about 5,700 years. To estimate the age of dead organic material, scientists use the following formula, which denotes the ratio of carbon-14 to carbon-12 present at any time t in years. Okay, so they give us this model the carbon dating model, which looks like this. It's R equals 1 over 10 to the 12th times E raised to the negative T over 8,223. Okay, so let's take a look at how are we going to figure out the age of a newly discovered fossil in which the ratio of carbon-14 to carbon-12 is 1 over 10 to the 14th. Well, we're going to plug in this 1 over 10 to the 14th. We're going to plug that in right here for R. So we're going to have 1 over 10 to the 14th equals 1 over 10 to the 12th times e to the negative t over 8,223. I would recommend that we multiply both sides of the equation by 10 to the 12th. So over here, this 10 to the 12th divides out with this 10 to the 12th. So on the right side of the equation, we're left with just e to the negative t over 8,223. And on this side, what is 10 to the 12th divided by 10 to the 14th? Again, I'm dividing two things that have the same base, so I need to subtract the exponents. So I'm going to have 10 to the 12 minus 14, that's 10 to the negative second, which is the same thing as 1 over 10 to the positive second, which is 1 over 100. So I should have 1 over 100 here equals e to the negative t over 8,223. Now, I'm going to have to solve that by rewriting in log form. So I'm going to write log to the base e of 1 over 100 equals negative t over 8,223. And I can write that as ln of 1 over 100 equals negative t over 8,223. And then to solve for t, I think I would multiply both sides of the equation by negative 8,223. So here, 8,223's divide out, and a negative times a negative is positive. So I get t equals negative 8,223 times ln of 1 over 100. So let's see what this looks like on our calculators. Negative 8,223. Negative, nope, let's try this again. Delete, delete, escape. Okay, negative 8,223 times, and I want the ln of 1 over 100. So control e to the x, ln, fraction templates, 1 over 100. So I think that's what it should look like, and I want to get a decimal approximation. So I'm getting 37,868 approximately. 37,868. 37,868. Right? Yep. Okay, so that would be the number of years old for this fossil. All right, is that what he's talking about? Yes, this newly discovered fossil would be about 37,868 years old. Okay, I am going to do one more example. I think I'm going to stop there for this video and end it at this point and have you work on some homework and work on some problems from the gift. Have a good day, everybody.